So welcome students, and in these last 2 weeks what we are going to do is concentrate on the a general linear non-linear equation. Okay, so consider this problem. Let's say consider the problem x prime equals to f of tx. So we have a system here, yes, and x at the point, let's say 0, equals to x naught. Is it okay? I mean, I am writing 0. You can substitute it by t naught. But anyways, let me just do it. Otherwise, you may get confused. So t naught, some point t naught. T naught can be 0 also. No problem. Okay. So we are looking at this equation. Now the thing is this. See, we know that let's say we are assuming f is smooth. Yes. So we know if f is C1, then around t naught there is a unique neighborhood where you have a unique solution, right? So essentially, what let me put it this way. So Picard's existence. Picard theorem, right? Existence uniqueness theorem, that is. What does it say? It says that there exists epsilon positive such that, so in T naught minus epsilon and T naught plus epsilon, okay, so there exists a unique, so maybe I can put it this way, such that there exists epsilon, there exists unique, okay, unique y or x, let's say x, which is from C1 of x is lies between C1 of T naught minus epsilon to T naught plus epsilon, okay, to Rn. Yeah, of course, this I wrote it as a open this closed set, but it is generally as a maximal interval of existence. We talked about it, right? It can be open also, so it will be open if you talk about that. Okay, so there exists an epsilon greater than 0 such that there is a unique solution satisfying 1. Satisfying 1. This is we know. Okay, now the thing is this: we talked about well postness of problem, right? Now the question is this question: when is this well post? Okay, so when is one well post? When is one well post? Okay, so in this next few videos we are going to talk about that sort of thing. So basically, existence uniqueness is guaranteed by Picard's theorem. Now the question is this: when is it well post? Means the third part, when is the solution stable? Okay, what do I mean by that? Okay, let's just understand this. Okay, so with an example, let's just understand this with an example. See, let's say we are talking about a problem like y prime equals to ay. Clear? This is the equation given to you. Okay, now, and with the initial data y0 equals to, let's say, y naught. Okay, now for this problem we know that there exists a unique solution, right? Unique solution y of x. I hope you can prove uniqueness, right? Which is y naught e power ax. So please check, how do you prove uniqueness? You have to check that part. Yeah, we did it. We did this thing while we proving, many a theorem. So basically, you don't need Picard to do this here. So please check this part. Check why the solution is unique. Yes. So we know that there is a unique solution yx which looks like y naught e power ax, and this holds for all x in R, right? This holds for all x in R. Please don't get confused between this capital X and this small x. This capital X, yes, is a function of t. T is in R. Okay, so please don't get confused here. Yes, that is our variable. Basically, the curve here is just a point. Now, the thing is this. Now, let us look at this. See, therefore, let's say that if you define, if we write like this, x, y as a function of x, initial data is 0, and at the point 0 it takes y naught. Let us write it this way. So in that way, if we do it, we can write it as it is y naught e power ax. Okay, this is the solution. I can write it like this. Yes, now you see, now we can do it like this. See, I will define delta y. Okay, what is delta y? Delta y is the change of y when y naught is going to be changed from y naught plus delta y naught. So basically, you see, if I change y at the point 0 to y naught, okay, and I change it to y naught plus a small increment on y naught, okay, what happens? we want to see how much is the solution changing, right? That's what stability is. Basically, we don't want our solution to fluctuate too much with this initial date change of initial data, right? Okay, so that's the idea. So basically what we have is this. See, what is delta y naught? The mod of delta y naught, we are defining it as the function y at x 0, so variable x at the initial data 0. And what is the what is y does at the point 0? It is y naught plus delta y naught, okay, minus y x 0 and y naught. So we want to see how much is the solution changing if you're changing the initial data. Now you can, of course you can see that since this is linear, that will give you delta y naught, the modulus of that, times e power x. Is it okay? This holds for all x greater than equal 0, right? Now this is a very simple equation, right? Now the question is this: if I'm saying that it is well posed or not, that is a tricky question. Why? Because see, note that if a, okay, is less than equal 0, yes, then you see e power ax, this actually, is basically decreasing, right? So basically what you happens is delta y, yes, that is equals to delta y naught times e power ax, okay. And if a is negative, I can make it less than epsilon, right, for all x greater than equal 0, provided delta y naught is less than epsilon. Is it okay? I can of course do this. If a is negative, e power ax, that can be made less than equal 1, and hence all of this is true, right? So you see, I can make delta y as small as possible, you understand? So basically whatever the initial data, however I am changing, the original solution is also changing proportionately, okay. But now see that if a is positive, is it okay? If a is positive, then delta y, okay, less than epsilon, this holds if and only if the increment of delta y naught, the modulus of that, should be less than epsilon times e power minus ax, okay. Now this is possible only for finite values of x, right? So you see, this is possible only for finite values of x. Is it okay? Because you see, the thing is, x, if it goes, I mean, you can take arbitrarily large x, this will actually push delta y naught to be towards 0, right? Okay, so I mean, no matter how small mod delta y naught is it okay? Yeah, so you do realize that in this case you cannot really say that this problem, you see, in 0 infinity, this solution is in 0 infinity, you can think of it like that, right? So this solution, in this case, it is stable, but in this case there is a issue, right? We cannot talk about this sort of stability, okay, right? So now let us put it this way. See, the thing is, without going into exact definition, yes, so basically what we are trying to do is this: when do we say some solution is stable? If a small change in the initial data brings only small changes in the solution, right? That is what we mean by stable. And if it is, of course, if it is not stable, it is unstable, so that sort of thing is there, okay. So in this case, you see, this case, what can you say? That it is unstable, okay. It is unstable. What is unstable? The solution is unstable, right? Yes. Or I mean, since this equation has only one solution, in some author may say the solution is, the equation itself is unstable in that sense, that the solution is unstable basically, okay, right? So with that, let me give you the definition of what stability means. Yeah, stability, what does it mean? A solution of what? Of one. Yes, this problem, okay. And a solution of one, how, what is defined? X, okay. So a solution x of t, our variable is t, yes. And how do we write it? It is x t, and the initial data in our case is t naught, okay. You can take it to be 0, it's not a problem. And then our initial data is x naught. Is it okay? You see, we are writing it like this just to make everything clear. Otherwise, you see, initial data is changing, right? So, I have to write x and another different function. So, we are just writing it like this. Okay. So, a solution this of the initial value problem 1, okay, is said to be stable. So please remember, this is not anymore a linear equation, but this is a non-linear equation. Is it okay? Is said to be stable. To be stable. Stable. When is it stable? If for each epsilon positive, okay, there exists delta. Which depends, of course, on epsilon and the initial data. Yeah, 0. So the initial point. Sorry, not the data. The point t naught. Okay. Of course, this is positive, delta positive. Okay, such that if your initial data, if you perturb it a little bit, so basically the change of x naught. Okay, if delta x naught is less than delta, okay, that will imply that x of t naught x naught plus delta x naught. Okay, so basically I'm looking at the solution corresponding to the initial data x naught plus delta x naught, and I'm taking the difference of that solution with t naught x naught. We are saying that should be less than epsilon. Is it okay? So given epsilon greater than 0, we can find a delta. So basically continuity kind of stuff. So if you are changing your initial data a little bit, you also expect your solution to change likewise, right? So that's your stability. Is it okay? Now let's look at the definition of instability. Now please remember, this is, I am saying the solution is stable, not the equation or something like this. Yeah, we are saying the solution is stable. This is the nomenclature which we are going to use. Okay. Now a solution x of t, which is given by x of t naught x naught. Is it okay? Yeah, this is of 1 is said to be unstable, right? Unstable. Okay, if of course it is not stable. If it is not stable, quite simple, right? When is it unstable? If it is not stable. So that is why the earlier definition doesn't hold basically. Okay, now with stability we have another beautiful definition which we are going to use. Stability has different aspects, right? Now this is another aspect. What is it? A solution x of t, which is defined by x t naught x naught, is said to be, so please remember this thing. The first one is stability, the second one is unstable, third one is said to be asymptotically stable. Okay, asymptotically stable. Okay, of 1, sorry, a solution of 1 is said to be asymptotically stable if, of course, it has to be stable. You see, by in the name itself we are saying it has to be asymptotically stable. So basically it has to be stable. So if it is stable, of course that is true, and there is the asymptotic part. So basically what I want is this, and there exists delta naught positive, okay, such that for the change in the data, okay, so delta x naught less than delta naught implies what? Implies this thing, x at the point t naught x naught plus delta x naught minus x at the point t naught x naught. Okay, see, what we are saying is this. First of all, it has to be stable. So basically this is true, this has to be true. Moreover, we also want, as for large enough x, okay, sorry, for large enough t, this must go to 0 as t tends to infinity. Is it okay? This is what our definition of asymptotic stability is. Basically, what we are saying is this difference is always less than epsilon. That is fine. It has to be for stability. So we want stability, but more than that, what we want is for sufficiently large t. Okay. We also want that the solution, the perturbed solution should converge to the original solution. Is it okay? So let's look at some of the with some examples what I mean by all of this. Okay. So first of all, let's look at this example. Example 1. Okay. So look at this equation, y prime equals to x. I'm not putting any initial data right now. Okay. Y prime equals to x. Now has a solution, has solutions of the form, solutions of the form. You can easily solve this problem, right? What is it? So let me write it down. Yx is, let's say, y at the point x naught, okay, minus x naught square by 2, okay, plus x square by 2. So basically, I want at the point x naught, it should pass through y, y at the point x naught should be y at the point x naught. So basically, yeah, that's the solution. Yeah, we want that. Okay. So you see, this is the solution, right? Any solution will look like this, right? Now you see that this is stable, of course. Huh? So the above solution is stable. Okay. Can you prove this? It is very easy to prove, right? I mean, of course, see, basically stability is nothing but like a continuity property. It's basically a continuity property, right? And you can see by this that this is just a function of it's a polynomial x square by 2 kind of thing. So of course you can show that this is going to be stable. It's not a issue. Okay, so please check this part, check it. Yeah, so I want you to do it. It's very easy, you can do it. So this is a form of equation where every solution is basically stable. Okay, so therefore every solution is stable. Solution is stable. Okay, now let's look at some other examples. Okay, now you see, let's say that every solution of y prime equals to 0, let's say. Yeah, how does it look like? Is of the form yx equals to yx naught, right? At any initial data, whatever the point is, yx equals to yx naught, that's your solution. Okay, now is it stable? Of course it's stable. I mean, there is nothing to prove here. It's by definition stable, right? Epsilon equals to delta. I mean, you do realize, right? It's basically a constant, right? It has to be stable. Yes, but is it asymptotically stable? See, the thing is this. If you look at it, y at the point x, here let's say x naught, y naught, sorry, y naught plus delta y naught minus y at the point x, x naught, y naught. Let us look at this. See, this is nothing but y at the point x naught. Okay, sorry, y at the point one second. This should look like this. Y at the point x naught is y x naught, right? So y with the initial data, so this is y naught, this is y naught. Okay, so with this, you see, you have y naught plus delta y naught, okay, and minus y naught. This is what we have. Okay, this is what we have. Now you see the difference is delta y naught. Okay, the difference is delta y naught. But you do realize that what is delta y naught? You see, y so one second, I did some mistake somewhere, no? Y at the point x naught. So basically it is, let's say it is, okay, so let's look at this. Yeah? You see, y prime equals to 0 and y at the point x naught is y naught. Okay, this equation we are looking at. So what is the solution? The solution is y x is y at the point x naught. That's the solution, right? Again, you see y prime equals to 0 and y at the point x naught is y naught plus delta y naught, right? So what is the solution? Yx equals to y at the point, sorry, this is y naught, and this is y naught plus delta y naught, right? That will be the solution. Yes, it's fine. That's what I wrote here. Yes. So you see, so basically this is the difference, right? Now if you're taking delta y naught less than delta, let's say, yes, less than delta, so basically epsilon equals to delta works, right? It's not a problem. If you choose an epsilon equals to delta works, so basically this will be less than epsilon, and which is equals to delta. So epsilon equals to delta works. So this is stable. This is stable. Okay, but the question is this, but you see, as t tends to infinity, does anything change? Nothing changes, because you see the difference is always delta y naught, right? So it is independent of x. So in this case t is x. Okay, so as x tends to infinity, you see this difference, yeah? Let's just say this is a. So norm of a is always constant, which is norm of delta y naught, right? It's independent of x. And so this is not going to 0. So this is not asymptotically stable. Not asymptotically stable. I hope this is clear. I'm sorry, I got confused a little bit. Okay, so I hope this is clear. So you see, this is an example of a solution, okay, of an equation where every solution is basically stable but not asymptotically stable. Okay, so you do realize that those two situations are different. Okay, now let's look at another example. Let us clarify more what happens. Okay, so you see, every solution of this equation, every solution of y prime equals to pxy, okay, is of the form, it's a linear equation, right? Is of the form. So basically you find the integrating factor and you solve it, yeah? And once you solve it, what you are going to get? Y at the point x naught exponential integral x naught to x, our initial data is at x naught, okay, p of s ds. This is what you are going to get, right? Now you see that if you just think about it this way, yeah, we are not now talking about all solutions, yeah, just one solution. Let's just see, we talked about whether it is stable or asymptotically stable, whether a solution is stable or not. Okay, so here we are saying that, you see, 0 is always the solution, right? If you think about it properly, 0 is always the solution for this problem. You see, for this problem 0 is always the solution. So you see, trivial solution is always there, yeah, for the equation. Now the thing is this, the trivial solution, is it stable? Do you think it is stable? It is of course stable. Trivial solution is of course stable. I mean, there is nothing to prove. It's less, I mean, it's trivial, right? What I mean is the trivial solution is stable. Checking that part is trivial. Yes, so it is trivial. So the trivial solution is stable. Okay, but what about asymptotic stability? But it is asymptotically stable. Let me write it this way. A is asymptotically stable. Okay, if and only if, when do you think it is asymptotically stable? See, if you write down this difference here, okay, what is going to happen? It is delta y naught exponential of this particular thing, right? Now you see, if the exponential of this particular whatever inside that goes to 0, okay, sorry, if that goes to minus infinity, this in exponential of this whole thing goes to 0, then we are in business. So basically what we want is this: it is asymptotically stable if and only if x naught to x p of s ds, okay, this is going to minus infinity as x goes to infinity. I hope this is clear. See, if the inside part of the exponential goes to minus infinity, so exponential of that thing goes to 0, right? So basically then I have that the difference a, this goes to 0. This is what we want. It has to go to 0 as x tends to infinity. Okay, so what we proved is, in this case the trivial solution is stable and it is also asymptotically stable if and only if this particular condition holds. Is it okay? Right. Okay, so now let's look at some theorems which will actually guarantee stability. Okay, some theorems. Theorem 1, let's just call it theorem 1. Okay, so what is this theorem? You see, it is saying that all solutions, okay, all solutions, one second, I think it is okay, right? What I wrote, yeah, it is okay. Yeah, so let me write down. You see, all solutions of the differential system of the initial value problem. Let me just put it this way: initial value problem. What is the problem? X prime equals to at times x. Okay, so we are in the realm of linear systems now. Okay, so for a linear system, what can we say? They are stable, because you see here all the examples which we gave are of linear systems essentially. Yeah, so x prime equals to at times x are stable. When is this stable? Let's just understand that first. Okay, if and only if they are bounded. They are bounded. So beautiful theorem, right? So you see, the thing is, you just have to find out the solutions. Yes, and you just have to make sure that the solutions are bounded. Yeah, if they are bounded, they are stable. Is it okay? Right. So what is the proof? So you do understand what I'm trying to say. Let's say if you have to find, if you can find a solution which is basically bounded, then you can say that the solution is stable. And what here this theorem says, that every solution is stable if and only if they are bounded essentially. Okay, right. So first of all, let's just start with this. Let's say that I have to show that the solutions are stable, right? So basically I start with all solutions are bounded. So let all solutions of x prime equals to at times x is bounded. Is it okay? Now if that is the case, we have, of course, if you have a linear system, right? Now you remember the fundamental solution, right? Okay, so we have a fundamental matrix of this differential system, right? So let's say phi of t is the fundamental matrix of this system. So I'm not writing all that. Is it okay? I hope you understood. Yeah, see, if all the solutions are bounded, that is given to us, right, and phi x is fundamental matrix, then there exists, we can say that there exists a constant c positive such that the norm of phi of t is bounded by c, right? Less than equal c, doesn't matter, less than c is less than equal c. Okay, this holds for all t greater than equal t naught. Okay, t naught is our initial data or any point, some point t naught. So essentially what we are saying is this, that if all solutions are bounded, phi t is a fundamental matrix, so we can actually put a bound on fundamental matrix, right? Why is it true? See, to be what is phi of t? Every column of phi of t is a solution of, is basically this thing, right? X prime equals to at times x, and x at the point what is it, t naught, let's say, is ei. Yeah, so there is a unique solution xi of t which is defined in whole of R in this case, and then I can write your fundamental matrix as x1 xn, right? That's the thing, which x1 is the full column, right? Now you see what is the norm of phi. You can just look at the Rn norm also, it's not a problem. Okay, the linear norm, exactly the same thing will happen. So basically, or you can also talk about the matrix norm. You calculate the matrix norm, you can of course check this part, that if each xi's are bounded, then the matrix norm is also going to be bounded. Okay, so please check this part. This we also used it in earlier also, if you remember, while talking about asymptotic behavior. Okay, so please check this part. This is very easy. Yes, this is very easy. So what did I use? The fact is this: every column of this matrix is bounded. Yes, It's given. That's the thing. You see, it said that every solution is bounded. So every column is bounded. You just have to show that the matrix is bounded. Yeah, I hope this you can do it. Now you see, so given epsilon greater than 0, given epsilon greater than 0, okay, we can choose delta x naught. Okay, how do we choose? So this is just a trick which I am using, but you will see why we can use it like this. See, epsilon by C times norm of phi inverse T naught. This is what we are using. Okay, let's just call it that is a delta which depends on epsilon positive. Okay, now why we are choosing it? So that, see, the point of choosing it is this x of t t naught x naught plus delta x naught minus x of t t naught x naught. If you look at this difference, okay, this difference is nothing but if you remember, it's a homogeneous problem, right? The solution is phi of t, phi inverse of t, and then t naught, sorry, phi inverse of t naught, and then delta x naught. That will be the solution, right? I hope you remember. Okay, again, let us do it. X prime equals to 80 times x. X at the point 0 is x naught. What is the solution? The solution is x0 equals to the fundamental matrix xt times c, right? Now if you calculate it, you see x naught equals to x at the point t naught, right? X at the point t naught, which is phi at the point t naught times c. So what is c? C is nothing but phi inverse t naught times x naught. Okay, so this difference is phi of t, phi inverse t naught. So what is x of t? X of t is phi of t, phi inverse t naught times x naught. I hope this is clear. Now you just calculate this thing. This is what we are going to get, right? Okay. So this is clear. Now see, the thing is, this particular thing, I can use the matrix norm. You remember in the first week itself we talked about this matrix norm. So phi of t is bounded by c. So I can write it as norm of phi of t and then norm of phi inverse of t naught and then norm of x naught. So please remember, this is Rn norm, and these are all, the first two are matrix norm. This is the Rn norm. Okay, right. Now you see, this is bounded by c, right? So this is less than equals c. Yeah, and I have norm of phi inverse t naught and norm of delta x naught. So you see, with this choice of delta x naught, if we choose it to be less than epsilon by this particular term, then we can show that this is less than epsilon. Is it okay? And therefore, what we can say is all solutions of x prime equals to 80 times x is stable. So I want you to understand one thing. You see, here I am using that all solutions has to be bounded. Okay. See, if you have this idea that there is some solution which is unbounded, we can't do this thing, because in that case we do not know whether the fundamental matrix will be bounded or not. Okay, so if we can do that, of course, if you can show that the fundamental matrix is bounded, everything can be done. It's not a problem. Okay, so essentially what it is saying is, we are assuming that all solutions are bounded, and then we can say that, oh, then all solutions are stable. Is it okay? Now let's look at the converse. Converse is what? That all solutions are stable. Okay, so let all solutions of x prime equals to 80 times x is stable, are stable, sorry, are stable. Okay, so what does it mean? It means that the trivial solution is stable. That implies that is the trivial solution, because you see, this is a homogeneous problem, right? So the trivial solution is also stable. Trivial solution is stable, right? It's stable, right? Okay, so what is the trivial solution? So basically that is x of t naught and corresponding to the 0 data, right? That is your trivial solution. So that is 0 is stable. Okay, therefore what can you say? Therefore, given epsilon greater than 0, given epsilon greater than 0, there exists a delta, okay, which depends on epsilon positive, such that if I am changing the data, the initial data x delta x naught a little bit less than delta, that will imply that x of t naught delta x naught, yeah. See this change, yeah. See, the first initial data is corresponding to 0. What is the second initial data? 0. I am parting it to 0 plus delta x naught. So the only difference is this, right? So this difference is nothing but phi of t, phi inverse of t naught, and then delta x naught. This is what we have. Is it okay? Now you see, this is of course less than equal c times. Sorry. What am I doing? Yeah, this is fine. Yeah, this is fine. No, this is not less than. This is the earlier case less than c. See, okay. So this is what we have. Okay, so we have that this particular thing is less than epsilon. Yeah, it is given, right? It is given that it is trivial. So basically, there exists for epsilon there is a delta such that this happens. Okay, we have this. Okay, now you see this delta x naught. This choice is on us, right? We can make it as small as possible, and we can take any vector we want, right? But sufficiently small, that is okay. So you see, now choose delta x naught. Okay, this we are choosing it to be delta by 2 the ej. What is ej? Ej is the jth unit vector in Rn. Is it okay? Yeah, so we are choosing it this. See, if we choose it like this, what is delta x naught? That will be delta by 2, which is, you see, which satisfies this, right? So I can choose this. Now once you choose it, what do we have? Then we have x of t, x inverse of t naught, and then delta x naught. This, yeah, we can write it as, this is nothing but let me just write it, and then I will tell you what I mean by this. Phi j of t times delta by 2. Okay, so here, where, what is phi j? Where phi j of t is the jth column of phi t, phi inverse t naught. Is it okay? Yeah, see this matrix, I am just we can just multiply it, and let's say that there will be a jth column, right? Let's just call that jth column as phi j of t. Yeah, we'll just call it, and delta x naught I can just bound it by delta by 2, right? So I can just write it like this. Now you see, this is less than epsilon. Okay, that is given to us. You see, this is given to us, so we are just writing this part like this. Okay, so we are choosing a particular vector delta x naught such that this is happening. So we have this epsilon. Clear? Therefore, what do we have? Therefore, it follows that norm of phi t, phi inverse t naught. Okay, this will be given by the maximum of phi j of t. J lies between 1 and n. That's the matrix norm, right? So basically, if you look at this matrix, phi t times phi inverse of t naught, then that matrix norm is given by maximum of these columns. Yes, that's just the definition, right? And that will can be written as 2 epsilon by delta. Yes, is it okay? You see, norm of phi j t is less than equal 2 epsilon by delta. So the maximum is also bounded by 2 epsilon by delta. Yes, this is what we can write. Now, if that is true, then you see, therefore, any solution, x of t naught, x naught of 1 looks like this, right? Can be written, is of form, is of the form. Let me write it this way: is of the form. How does it look? Okay, maybe I can write it as satisfies, it will be better. Satisfies norm of x t naught x naught. Okay, this norm is nothing but norm of phi of t, phi inverse of t naught, and then uh, x naught. Right now, that the first thing, you can take this matrix norm, that definition is there, right? So we can use that matrix norm inequality, and we can write this is definitely less than 2 epsilon by delta times the norm of x naught. Is it okay? I can write it like this, and therefore of course, see, delta x naught, that is bounded, right? That's just some vector. So therefore all solutions are bounded. Okay, so please remember the theorem which we did here now is this. We are saying that for a variable coefficient equation, if you have that all solutions are bounded, then all solutions are stable, and vice versa. Okay, so both of them are true. Is it okay? Now you see, the thing is, there is a small corollary which you can write here. See, if the real part of the multiple eigenvalues of A are negative. Okay, so basically when we have, this is the case of constant coefficient equation. Okay, and the real part of the simple eigenvalue okay, of A are non-positive. Okay, then all solutions are stable. Okay, see, first of all, you start with a matrix. Let's say, let's look at the simple case. So let's say if you have a matrix with all 2 cross 2 matrix, yes, and you have 2 distinct eigenvalues, both of them are non-positive. Okay, so basically negative, let's just say. Yeah, now what happens is, you can see that the solution, you can write it as c1 times e power lambda 1 t plus c2 times e power lambda 2 t v1 v2, right, with the corresponding eigenvectors. Now you can see that the difference, if you look at the difference of two solutions with the part out this thing initial data, you can see that you can make it as small as possible. So basically this goes to 0, right, in that case. So in this case it is stable. Right, now what we are going to do is, we are going to give a necessary and sufficient condition. Necessary and sufficient condition for the system x prime equals to 80 times x, this system, okay, to be asymptotically stable. Okay, so let's look at that. So the first thing we proved is when it is stable. So basically if they are bounded. Now what about asymptotically stable? So the theorem says, theorem 2, let phi of t be the fundamental matrix of the system. I am not writing the whole thing, fm, a fundamental matrix of x prime equals to 80 times x. Is it okay? Then all solutions let's call this system as star, it will be better. Then all solutions of star are asymptotically stable, AS. Let me write it AS, asymptotically stable, if and only if norm of phi t, this goes to 0 as t goes to infinity. Is it okay? Yeah, we can prove this. So basically what I am saying is this: when is it asymptotically stable? If the fundamental matrix, the norm of the fundamental matrix, that goes to 0. That's okay. Okay, so proof. First of all, let's say that this system, the star, any solution, how does it look like? So any solution of star is of the form x of t, t naught, x naught is phi of t, phi inverse t naught times x naught. Okay. Now see, since phi of t, this we talked about it, right? This is continuous. This is continuous, right? Why it is continuous? See, phi is what? Phi is the fundamental matrix, and every component, so every column of the fundamental matrix, that is basically a continuous function. It's basically continuously differentiable, right? Curve. So phi is definitely continuous. Yeah. What does it imply? Then that implies, since it is continuous and it goes to 0, you see, it goes to 0. Yeah. And norm of phi t goes to 0 as t tends to infinity. So that will imply that there exists C positive such that norm of phi t can be made less than equal C for all t greater than equal, let's say, t naught. Is it okay? See, the thing is, let's say that from t naught to some number t1, it is a closed bounded set. So in that closed bounded set, since phi is continuous, it is bounded, right? So you can make it less than equal some bound. And after t1, so since this goes to 0, so after some sufficiently large t1, norm of phi t can be made less than epsilon. So basically you take the maximum of epsilon and the first bound, then we can say that there is just this such that this happens. I hope this is clear. Okay. Now thus what do we have? Thus norm of x t, t naught and x naught, this is can be written as dominated by C times norm of phi inverse T naught norm of x naught. This we can do. Yeah. And then, and hence every solution is bounded. It's bounded, right? See, once the fundamental matrix is fixed at the point t naught is some fixed point, right? So phi inverse t naught, that is a fixed matrix. So the norm is fixed. We know what the norm is. Okay, that's the constant. And norm of x naught is also fixed. So therefore, what happens is every solution has to be bounded. Okay. Now the thing is this: since every solution is bounded of this C, we can use theorem 1, and that will imply, and by theorem 1, all solutions are stable. Okay. Now what happens now? So therefore we have to now again we have to show that they goes to 0, right? The difference. So you see, norm of x of t naught x naught plus delta x naught minus x of t naught x naught, this difference yeah, is nothing but phi of t, phi inverse t naught times delta x naught, right? Now this is again bounded by phi of t, phi inverse of t naught delta x naught here, and you see this goes to 0 as t turns to infinity. Is it okay? So therefore every solution of star is asymptotically stable. Again, I am not writing it properly, but AS is asymptotically stable. I hope this is clear. Yeah? So you understood this particular term, right? See, phi of t, it is given, it goes to 0 as t tends to infinity, right? So, and this is bounded. So basically, this is a bounded term, and this bound term goes to 0. So the whole term goes to 0. I hope this is clear. Yes. Okay. Now, what about the converse? Converse. Conversely, let's say that if all solutions are asymptotically stable, are asymptotically stable. So I am writing it as AS, right? Then the trivial solution will also be asymptotically stable. Then the trivial solution, okay, what is it? It is x of t, t naught, 0. Because the trivial solution will be corresponding to the 0 boundary data, right? So that equals to 0 is asymptotically stable. All solutions are asymptotically stable, so the trivial solution has to be, right? Therefore, what is norm of x of t, t naught, delta x naught? What is it? You see, this is nothing but this in that case uh, goes to 0 as t tends to infinity. Clear? Uh, Therefore, so you see, if this goes to 0 as t tends to infinity, okay, see, the trivial solution is asymptotically stable. So basically, in the trivial solution, I mean, the difference then must go to 0 as t tends to infinity. That's just the definition that will imply this. I should write it like this. So this is the definition. Now, if this is the case, therefore, what is this? This is nothing but x of phi of t. So this is nothing but phi of t, phi inverse of t naught, and delta x naught. This goes to 0. That will imply this goes to 0 as t tends to infinity. Okay. If this is the case, therefore, norm of phi t has to go to 0 as t tends to infinity. There is no other way, right? Yes, since the whole term, this term, it goes to 0 as t tends to infinity, you can just put it as epsilon delta. So you can just do that. Please check this part, and you can show that norm of pt can be made less than epsilon, okay, for a particular choice. Since this goes to 0, norm of pt can be made less than some particular choice of epsilon. You can do that, and you can show that this goes to 0, since this goes to 0. Is it okay? Right. So hence it is proved. So essentially what we showed is this: the asymptotic stability depends on the norm of the fundamental matrix. If it goes to 0, we have asymptotic stability, otherwise we don't. Okay. Now you do realize that for a constant coefficient equation, if the eigenvalues are basically negative, then what happens is you essentially have asymptotic stability. Okay. So I will put it in the assignment also. You can check it there. I'm not writing this as a part of corollary, but it is clear, right? Okay, so for constant coefficient, please check when we have asymptotic stability. Okay, right. Now what we have is this: we will talk about another type of stability, and then we are going to end this lecture. So the stability is called another new definition. So we have, first of all, just stability, stable, solution stable. Next, we have something called the asymptotically stable. Yes, Now we have something called a uniformly stable. So a solution, by the name of it, you do realize what I mean by this, right? A solution x of t, which we write it as x of t, t naught, x naught, is said to be uniformly stable. See, this stability, as you can understand, this is basically a, we are taking the definition of continuity and we are just morphing it into our needs. Okay, so here what we are going to do is basically we are going to change the definition of continuity to uniform continuity. So the solution xt equals to x of t, t naught, x naught is said to be uniformly stable if for each epsilon positive, okay, there exists a delta. Yes, please remember, this delta depends only on epsilon positive, okay, such that any solution any solution yeah, I am this writing it in a little generalized way. So what I'm doing is this, I'm writing x1 of t. Okay, what is x1 of t? It is given by x evaluated at the point t, at with the initial point at the point t naught, and the initial data is x1. Okay, uh, of the problem. So please remember the stability exam definitions which I am giving it for a general nonlinear equation, okay, not only for linear equation of the problem. X prime equals to f of tx, x at the point t naught is x1. Okay, I should write it like a solution x of t of this problem. X prime equals to f of tx, x at the point t naught is x naught, is said to be uniformly stable if with this initial data, uh, yeah, the inequality uh, t1 greater than equal t naught, and if x1 sorry e1, this we called it as x1, we called it as x1, right? Okay, so let's just write it x1 at the point t, yeah, which is given by this, right, minus x at the point t. This difference is made less than epsilon for all t greater than equal t1. I hope this is clear. Okay, so what we are basically saying is, see, this is just a definition of uniformly stable. What we are saying is this: if you have this solution, okay, your initial solution, and then you have this problem with the initial data as x1, okay, then this solution, the original, the resulting solution with the initial data x1 and the original solution x of t, that can be made less than epsilon, that's all. Okay, and this holds for every epsilon. You can actually find a delta such that this holds. Okay, I forgot to write what delta is here. One second, I should write it. Sorry about it. Yeah, the definition, that is why. Okay, so and norm of x1 x1 sorry, x1 of t1 minus x of t1 less than delta implies this. Okay, see, if t1 is confusing you, what you do is you choose t1 to be t1 to be t naught, huh? No problem here. So what we are doing is this, I am saying that you can change your initial point also, not only initial data, you can change the initial point also. But for now, let's just assume that if t1 equals to t naught, okay, in that case, the difference of those two, if it is less than delta, then the difference of the solution can be made less than epsilon. Okay, for all t greater than equal t naught. Why it is uniform? Because the delta which you are going to get, that will be dependent only on epsilon and nothing else. Is it okay? Right. Okay, so let's look at an example that will make life easier for us, right? So every solution of y prime equals to 0, okay, is of the form yx is given by y at the point x0, right? If it passes through the point x0, it has to be yx equals to y. So do you think it is uniformly stable? Exactly, this is actually uniformly stable. It's very easy to see, right? So it is easy to check. So please check this part. Easy to check that every solution is uniformly stable. Is uniformly stable. Uniformly stable. Yes. Please just write down this definition and see that it is uniformly stable. This is very easy to do. I am not doing that. But we have already seen that this is not asymptotically stable, but not asymptotically stable. Is it okay? So this is an example where the thing is, of course, if it is uniformly stable, it has to be stable. That is there. But the thing is, it may not be asymptotically stable. Is it okay? Yeah. So let's look at this is the last theorem which I am going to do before we finish this particular lecture. The theorem 3. Okay. What is that thing? So let phi of t be the fundamental matrix. Fundamental matrix. I will write it as f of m. Fm fundamental matrix of the system x prime equals to 80 times 6. So for linear systems, let's just understand when we have a sufficient and necessary condition for some system to be, for all solutions of the system to be uniformly stable. So let phi t is a fundamental matrix. Okay, then all solutions of x prime equals to 80 times x, right? All solutions are uniformly stable, if and only if, okay, you need a different condition now. So the condition which you are going to need is the following. So you remember in the last this thing, not last or maybe some 2-3 lectures back, we talked about a particular condition. Okay, so the condition will look like this. See, if and only if norm of phi t, phi inverse of t, sorry, phi of t, phi inverse of s, this is less than equal c for t greater than equal t naught, less than equal or maybe I should write it as s, s less than equal t, and which is less than infinity. You remember this thing we talked about when we talked about boundedness, right? You remember all solutions are bounded, and that is the condition, right? Okay, when we talked about asymptotic stability, so this is that same condition. Yeah. So when is it uniformly stable? If and only if this particular condition holds. Okay, so this is the theorem. Right now the thing is, what I'm going to do is this one part I will leave it for yourself. So basically the thing is, check this part. This you have to do it yourself. Check that if all solutions are uniformly stable, if all solutions are uniformly stable, okay, then the trivial solution is uniformly stable, right? Yeah. So use this to show that this condition, phi of t, phi inverse of s ds, phi of t, phi inverse of s, this is bounded. Okay, so please do this part. Yeah, I want you to do this part yourself. Okay, I will show you just this part, that what happens if this condition is holds. Okay, then I will show that they are uniformly stable. Okay, so conversely, this part I will do it. Conversely, let's say that let x of t, which is given by x of t, t naught and x naught, solves x prime equals to 80 times x. Is it okay? Yeah. Then for, you see, t1 greater than equal t naught. Yeah, we have to show that t1 t naught. See, for t1 greater than equal t naught and this particular delta condition, we have to show some, that is x1 minus x has to be less than epsilon, right? So for t greater than t naught, huh, you have x of t. I can write it as phi of t, phi inverse of t1, and then x of t1, right? I can do it like this. See, this is our new initial data at the point t1, right? Now, if x1, I wrote it x1 like this, or I wrote it like this. Huh? So let us write it like this. x1 of t, which is in our case, you see, x1 of t satisfies this thing, this problem with initial data at the point x1. Huh? So if x1 of t satisfies this thing, phi of t, phi inverse of t1, and then x1 at the point t1. Is it okay? So is any other solution, is any other solution, and let's call this as double star condition, huh? And double star holds, what can we say? What we can say is this. See, x1 of t minus x of t, this is nothing but, this can always be dominated by phi of t, phi inverse of t1. This is common in both, right? And then I have x at the point t1 minus x1 at the point t1, right? I can say this. Yeah. Now you see, this can be made less than equal c times, because this is less than c. See, this is given less than c times x at the point t1 minus x1 at the point t. It is okay, I hope. Yes. Now see that this holds for all t naught dominated by t1, which is dominated by t, which is finite. Okay. Thus, if epsilon greater than 0, that is given, right? Epsilon greater than 0, then t1 greater than equal t naught, and the initial data x1 at the point t1 minus x at the point t1 less than epsilon by c, which will choose it as delta positive, implies norm of x1 of t minus x of t is less than epsilon, right? See, this is what we need to see. X1 of t1 minus x of t1 less than delta. You see, we chose it like this. So delta, we choose it like epsilon by c. If we do that, then of course, if this is epsilon by c, c and c gets cancelled out, so it will be less than epsilon here. And hence what happens is, then the solution, therefore the solution is uniformly, solution is uniformly stable. Is it okay? Yeah. So it's not very difficult to actually prove something is uniformly stable. This is how you do it. Yes, you just use the definition. That's all. Huh? It's not very difficult. So with this, I am going to end this video.